Good morning, everybody. Welcome back. I hope you all had a good weekend. That you got to get some rest, got to relax, got to do something fun maybe. And again, hopefully it wasn't all spent doing homework or working. But if it was, hopefully it wasn't too bad. All right. So today we're going to be getting into section 11.2. This lesson will be a little bit longer than the 11.1 lesson. We will go over two inference methods, also using the Chi-Square Statistic. 11.1 was using the Chi-Square test for goodness of fit. The next two Chi-Square tests will be for homogeneity and independence. Okay, so we'll take a look at those two different tests. Those are significance tests, so we will be doing hypotheses, significance levels, p-values, and we'll be using table C, which also involves degrees of freedom. All right, so that's the idea for today. All the resources for chapter 11 should be available now in Canvas. So you have the study guides, practice problems, and solutions are all there for section 11.1 and 11.2. Right, so all of that stuff is ready to go. Also, I updated grades yesterday. I think there's just one submission that came in later in the day yesterday, so it wasn't part of my update. So it should be as updated as possible. So that includes placeholder grades for the chapter 10 assessments. Right, considering how little time we have left in the semester, I want you to have an idea of what your grade is before the last set of assessments that will come up. Right, because we'll only have one more pair of assessments for the last few chapters that we're going to cover. So please, if you're not sure what your grade is, you should definitely go check in Canvas, or you can check in Synergy if that's what you prefer to use. They should be the same. If they're not, please let me know. That's an error on my end that I need to fix. All right, so there's that. Are there any questions before we begin? All right, then we will begin. Let's do that one and share. And that's going to be that screen. All right. All right, so here we are, chapter 11. All right, this is the second section in chapter 11, 11.2. We're doing inference for two-way tables. Our goodness of fit test from section 11.1 dealt with one-way tables. Right, we're looking at the data from a one-way table having to do with one variable, one categorical variable, and seeing if our sample fit with the null hypothesis or the assumed distribution. The next two have to do with two-way tables. One is to see essentially if the two-way table from our sample fits with the proposed or claimed distribution of the two-way table. The other one is to test for association. So we have two different tests dealing with two-way tables. Here's what we're going to work on today. We have the first one, compare conditional distributions for data in a two-way table, state appropriate hypotheses, and compute expected counts for chi-square tests based on data in a two-way table. We need to be able to calculate the chi-square statistic, degrees of freedom, and p-value for a chi-square test based on data in a two-way table. Perform a chi-square test for homogeneity, perform a chi-square test for independence, and choose the appropriate chi-square test for a given situation. Right, the two sample Z procedures of chapter 10 allow us to compare the proportion of success in two populations or for two treatments. What if we want to compare more than two samples or groups? More generally, what if we want to compare the distributions of a single categorical variable across several populations or treatments? We need a new statistical test. The new test starts by presenting the data in a two-way table. Two-way tables have more general uses than comparing distributions of a single categorical variable. They can be used to describe relationships between any two categorical variables. So we're going to be working with a lot of two-way tables in this section. All right, comparing distributions of categorical variable. Market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a Mediterranean restaurant compared 3 randomly assigned treatments, no music, French accordion music, and Italian string music. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. And these are their results. All right, so their type of music is essentially the treatment in our experiment. And then we have the categories of French, Italian, or other, as far as the entree ordered. Problem, we want to calculate the conditional distribution in proportions of the entree ordered for each treatment. So when no music was playing, the distribution of entree orders was French 0.357, Italian 0.131, and other 0.512. When French accordion music was playing, the distribution of entree orders was French is 0.520, Italian 0.013, and other was 0.467. And with our Italian string music, the distribution of entree orders was French being 0.357, Italian 0.226, and other 0.417. So we have this little breakdown here between the 3 treatments. Is there any questions so far? So we can also make an appropriate graph for comparing the conditional distributions in part A. This is a bar graph. Right? There's 3 different ones, one for each of the music types and the distribution of entrees ordered. This can make it a little easier for us to compare these things. All right, part C, write a few sentences comparing the distributions of entrees ordered under the 3 music treatments. Right, the type of entree that customers buy seems to differ considerably across 3 music treatments. Orders of Italian entrees were very low, 1.3% when French music is playing, but are higher when Italian music or no music is playing. French entrees seem popular in this restaurant as they are ordered frequently under all music conditions, but notably more when French music is playing. For all 3 music treatments, the percent of other entrees ordered was similar. All right, so essentially we're kind of trying to make a statement about how each of the treatments affect each of the different entree choices. Problem of how to do many comparisons at once with an overall measure of confidence in all our conclusions is common in statistics. This is a problem of multiple comparisons. Statistical methods for dealing with multiple comparisons usually have 2 parts. Number 1, an overall test to see if there is good evidence of any differences among the parameters that we want to compare. And number 2, a detailed follow-up analysis to decide which of the parameters differ and to estimate how large the differences are. The overall test uses the familiar Chi-Square Statistic and distributions. All right, so we're going to be specifically looking at this first step here. So we have expected counts and the Chi-Square Statistic. Chi-Square test for homogeneity begins with the hypotheses, null hypothesis. There is no difference in the distribution of a categorical variable for several populations or treatments. And the alternative, there is a difference in the distribution of a categorical variable for several populations or treatments. Very similar to how we write the null and alternative hypothesis for a goodness of fit test. The idea is to write essentially there is no difference in the distribution of whatever the claim is, whatever the thing is. And then for the alternative, say that there is a difference and write the same exact thing again. Right, we compare the observed counts in a two-way table with the counts we expect if the null hypothesis were true. All right. Consider the expected count of French entrees bought when no music was playing. All right, so we have 99 out of 243 times 84. Right, and these numbers come from the total amount of French entrees ordered across all music types. Right, divided by the total number of entrees ordered in the restaurant times the total number of entrees ordered with no music. So the values in the calculation are the row total for French, the column total for no music, and the table total. We can rewrite the original calculation as 99 times 84 divided by 243, and that is 34.22. Okay. Right, so essentially the 34.22 is the expected number of French entrees ordered when no music is playing in this restaurant. Is there anything I can clarify about this calculation? Good. Does anyone need a moment to write anything down? Okay. Here's some general ideas here. Finding our expected counts. When the null hypothesis is true, the expected count in any cell of a two-way table is the row total times the column total divided by the table total. All right, so you need to do this calculation for each entry in a two-way table. We also have our conditions for performing chi-square test for homogeneity. That is our randomness condition. The data come from a well-designed random sample or from a randomized experiment. We have our 10% condition with sampling without replacement. We need to check that the sample size is less than or equal to 10% of the population size. And again, our large counts, all expected counts are greater than 5 for the entire two-way table, excluding the column and row totals. Right? Obviously, if all the entries are greater than, or at least 5, then those will be as well. Would anyone like a moment to write any of this down for their notes? All right, so we have our expected counts here. Just as we did with the chi-square goodness fit test, we compare the observed counts with the expected counts using the statistic chi-squared equaling the sum of the observed minus expected squared divided by expected. This time the sum is over all cells, not including the totals in the two-way table. All right, we do not include our totals here. All right, so we have our observed counts here and our expected counts. Again, here's those same two tables. And for the French entrees with no music, the observed count is 30 orders and the expected count is 34.22. The contribution to the Chi-Square statistic for this cell is 30 minus 34.22 squared over 34.22, which is 0.52. And that's just from the first entries here in the table. We have 8 more. Chi-squared statistic is the sum of 9 such terms, right? We have a 3 by 3 table essentially. So our chi-squared is the observed minus expected squared over the expected, a sum of all those. We have 30 minus 34.22 squared over 34.22, and so on until we get to the end. Right? If you are using your calculator to essentially get the chi-squared statistic, it is sufficient to write the beginning of the calculation here, show the first couple terms, the last term, and put these little dots in between to show that you're using the proper procedure. And then you can just have your calculator do the work. Ultimately, we get a chi-square equal to 18.28. Is there anything I can clarify here about calculating our chi-square statistic? And then we need our p-value. So earlier we stated a significance test of the null hypothesis. There is no difference in the true distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. The alternative is that there is a difference in the true distributions of entrees ordered, and it's the same exact statement again. All right. This was our observed counts. We already checked that the conditions are met. Our calculated test statistic is chi-squared equaling 18.28. We need to use table C to find the p-value. We can use our calculator, chi-squared CDF command, to get an exact value. Because the two-way table has 3 rows and 3 columns that contain the data from the study, we use a chi-square distribution with degrees of freedom equaling 3 minus 1 times 3 minus 1, equaling 4. So it's 1 less than the number of rows times 1 less than the number of columns to get the degrees of freedom. And then we find the p-value using table C as we have. We have our little section of table C, degrees of freedom 4, right? That 18.28 value goes between 16.42 and 18.47, which means our p-value is between 0.001 and 0.0025. Again, so the chi-square equaling 18.28 falls between the critical values 16.42 and 18.47. Corresponding p-values between 0.0025 and 0.01. I don't know why they have different values here. Using the calculator, we get the command chi-squared CDF. We have our chi-square statistic essentially as the lower bound, 1,000 as that upper value, and that's because our chi-square distribution always is a greater than distribution, so we always just kind of have an unlimited upper bound for the most part. We could have one, but not in this case. And then our degrees of freedom, and we get 0.0011. Yeah, that's supposed to have another 0 in it. Anything I can clarify so far here? Okay, we want to interpret the p-value from the calculator in context. That is different than writing a conclusion. We're asked to interpret the p-value in context. Right, so assuming that there is no difference in the true distributions of entrees ordered in this restaurant when no music, French quarter music, or Italian string music is played, there is a 0.0011 probability of observing a difference in the distributions of entrees ordered among the three treatment groups as large or larger than the ones in the study. That is what our p-value represents. Right, that's the interpretation of the p-value in context. We can also write a conclusion based on the p-value. Because the p-value 0.0011 is less than our default alpha equaling 0.05 significance level, we reject the null hypothesis. We have convincing evidence of a difference in the distributions of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. Furthermore, the random assignment allows us to say that the difference is caused by the music that's played. Okay. So that is the difference between a conclusion and interpretation of the p-value. There's a distinction between those two things. So this is in a nutshell, what our chi-square test for homogeneity is. Suppose the conditions are met. You can use the chi-square test for homogeneity to test the null hypothesis that there is no difference in distribution of a categorical variable for several populations or treatments, versus the alternative that there is a difference in the distribution of a categorical variable for several populations or treatments. Start by finding the expected count for each category, assuming that the null hypothesis is true. Then calculate the chi-square statistic, the same as we have previously, where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, chi-square statistic has approximately a chi-square distribution with degrees of freedom equaling the number of rows minus 1 times the number of columns minus 1. The p-value is the area to the right of chi-squared under the corresponding chi-square density curve. So this is how we conduct our test for homogeneity. Would anyone like a moment to write any of this down for their notes? Please raise your hand. All right. And then we do a follow-up analysis because we did find significance. The chi-square test for homogeneity allows us to compare the distribution of a categorical variable for any number of populations or treatments. If the test allows us to reject the null hypothesis of no difference, we then want to do a follow-up analysis that examines the differences in detail. Start by examining which cells in the two-way table show large deviations between the observed and expected counts. Then look at the individual components to see which terms contribute most to the chi-square statistic. So we have this kind of generated data table here. We have our observed, our expected, and contribution to the statistic. All right, looking at the output, we see that just 2 of the 9 components that make up the chi-square statistic contribute about 14, almost 77% of the total chi-square 18.28. Right, having to do with French and Italian music, and I think ordering Italian. Right. We are led to a specific conclusion. Orders of Italian entrees are strongly affected by Italian and French music, because those had the largest, essentially largest deviations, largest variance, biggest difference. Right. And so this is our follow-up analysis since we found a significant result. There's no need to do a follow-up analysis if you do not find a significant result. If you fail to reject the null hypothesis, there's no follow-up needed. Anything I can clarify? Are there any questions? So now we're going to switch gears a little bit and do our test for independence, which is checking for association, relationships between categorical variables. Another common situation that leads to a two-way table is when a single random sample of individuals is chosen from a single population and then classified based on two categorical variables. In that case, our goal is to analyze the relationship between the variables. Our null hypothesis is that there is no association between the two categorical variables in the population of interest, and the alternative is that there is an association between the variables. So in the previous two tests, our hypotheses had to do with there being a difference or there not being a difference. That was our goodness of fit and our test for homogeneity. Now we're looking at there is an association or there is no association. The null hypothesis that there is no association. The 10% and large counts conditions for the chi-square tests for independence are the same as for homogeneity tests. There's a slight difference in the random condition for the two tests. A test for independence uses data from one sample, but a test for homogeneity uses data from two or more samples or groups. Right, so in this case, we have the random is that the data come from a well-designed random sample or from a randomized experiment. For the previous randomness condition, they had to be from two independent samples or independent groups. They can't be from the same sample or same groups. And we got 10% with sampling without replacement, and large counts, all expected counts are greater than 5. Right, but again, we have random, 10%, and large counts conditions that must be verified. Here's the rundown on how we do a chi-square test for independence. Suppose the conditions are met. You can use a chi-square test for independence to test the null hypothesis. There is no association between two categorical variables in the population of interest, and the alternative, there is an association between two categorical variables in the population of interest. You need to find the expected count for each category, assuming that the null hypothesis is true. These counts are found the same way as we did for the previous test. Right, then calculate the chi-square statistic, same way as we have previously. The sum of the observed minus expected divided by expected, where the sum is over all cells, not including totals, in the two-way table. If the null hypothesis is true, the chi-square statistic has approximately a chi-square distribution with degrees of freedom equaling number of rows minus 1 times number of columns minus 1. So the degrees of freedom is found the same way regardless of what type of two-way table or type of analysis you're doing with your chi-square test. Right, the p-value is the area to the right of chi-squared under the corresponding chi-square density curve. Right, so essentially the way we run this test is basically the same as what we just saw. The only difference is essentially the context. In this case, we're dealing with a single population or a single group. Right, previously, we were looking at several populations or groups that we're sampling from. Does anyone need a moment to write anything down? All right. So are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write Narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of the students said that some of the fright symptoms are still present when they are awake. Following table breaks down these results by gender. So we have this table, gender, and fright symptoms. Minitab is a program that can produce these types of tests with given data. We don't have access to Minitab, but the people with the textbook do. All right, so we have our chi-square test, male, female, expected counts are printed below, observed counts, chi-square contributions are printed below expected counts. So we have observed, expected, chi-square contribution. Okay. We essentially have 4 entries into this table. Our chi-square is 4.028. Degrees of freedom is 1. P-value ends up being 0.045. Okay. This is just all the data that we'll need for the problem. So assume that the conditions for performing inference are met. Explain why a chi-square test for independence and not a chi-square test for homogeneity should be used in this setting. The data were produced using a single random sample of college students who were then classified by gender. They had lingering fright symptoms. So we're sampling from a single population and from a single random sample. Right? The chi-square test for homogeneity requires independent random samples from each population. Right? So we could have done a similar type study, but sampling randomly from a population of males at the school and a population of females, and so kind of creating a separation before sampling. But because this was from a single random sample, from a single population, right, those are not independent samples as they need to be for a test for homogeneity. Is there anything I can clarify about this? So next, we want to state an appropriate pair of hypotheses for researchers to test in this setting. All right, so we have the null hypothesis. There is no association between gender and ongoing fright symptoms in the population of college students. And then our alternative is that there is an association between gender and ongoing fright symptoms in the population of college students. Again, I want to point out the only difference between these two hypotheses is that one says there is no association and one says there is an association. After that point, it's a copy paste of the same phrase. Okay. Which cell contributes most to the chi-square statistic? In what way does this cell differ from what the null hypothesis suggests? Right, men who admit having lingering fright symptoms account for the largest component of the chi-square statistic. Right, 1.883 of the total 4.028. Right, it's almost twice as large as the next largest one. Far fewer men in the sample admitted to fright symptoms, 7, than we would expect if the null hypothesis were true, 11.69. We want to interpret our p-value in context, what conclusion would you draw at alpha equaling 0.01? So they provided us a significance level, so we have to compare to that. If gender and ongoing fright symptoms really are independent in the population of interest, there is a 0.045 chance of obtaining a random sample of 117 students that gives a chi-square statistic of 4.028 or higher. That's an interpretation of the p-value. The conclusion comes next. Because the p-value 0.045 is greater than 0.01, we fail to reject the null hypothesis. We do not have convincing evidence that there is an association between gender and fright symptoms in the population of college students. Is there any questions about this example? Is there anything I can clarify? All right. That brings us to the conclusion of the slides, all right? So we've seen 3 different types of chi-square tests. One having to do with a one-way table, that was 11.1, and 2 different tests dealing with two-way tables, all right? The test for homogeneity, sampling from 2 separate populations or groups, checking to see if there is or is not a difference between those groups or populations, right? Our chi-square test for independence is testing for association within a single sample or a single group or population between 2 different categories. Okay. The way in which we calculate the expected values and the chi-square statistic is the same for both tests. There's no separate procedure, it just depends on the context and then how we interpret those results. Okay. Is there anything else I can clarify here? Are there any questions? All right. Stop sharing the screen there. Okay. So then that's essentially the notes for section 11.2. We're going to do an activity again tomorrow to practice more with our chi-square statistics and chi-square tests. And hopefully that'll help things make more sense again. I think I'll probably do a Desmos activity once again, because I think those allow us to kind of do the math a little easier than Pear Deck or other types of things. So we'll have that ready for tomorrow. And then next week, hopefully we'll be able to get through chapter 12, get some practice in with that. And then I'll try to decide how much of chapter 3 I want to include. I need to decide how much of 12 and 3 because we need to review as well. So that's kind of what we're looking at here. Are there any other questions, comments, concerns about anything with the class? All right, so last little note here, if you have still not check to make sure that your the 2021 AP testing app, right? The digital testing app, if that is installed on your computer, if it works on your computer, if you're taking the AP exam for this class or any other class, you need to do that. There are some, if you're using a school computer, some of them are too old to run the app. Better you find out now when you can get a computer replaced than the days before the exam when it might be really stressful. Right, I know that there's still a chunk of you who have not logged into that testing app. You need to try to open it and log in to confirm that it has downloaded properly and that it works. Right, that is a must-do thing. You should do that like today. Double check to make sure things are working so that if they are not, you can arrange to get a different computer from the school or whatever you need to do. Okay? So please do that. All right. And with that, that's all that I have for you guys today. We'll get some practice in on this stuff tomorrow. Have a great rest of your day, and I will see you tomorrow.